So this is a video editorial for the LeetCode weekly contest 482. I'd say the problems were fairly straightforward this time as well. Even though it says that Q4 is a 7-pointer, I found it like it's just a straightforward application, which I would have solved in like less than 5 minutes there was not the if I didn't make the silly implementation error I did, which will be visible in the screencast obviously. So yeah, if I'll timestamp the different sections of the tutorial and the screencast, the live solve solution, so you can jump around wherever you want to in the video. So this problem basically states that in the first problem, the problem basically states that in a simplified version, basically we given an array, we need to find an index I such that the prefix sum, let the prefix sum from here to this index I be x, and the suffix minimum from the index I plus 1, this is I, right, and this is I plus 1, the suffix minimum from I plus 1 to n minus 1 be y. Then the score for I is x minus y, and we just had to find the maximum possible score. So here obviously the constraints for I were less than equal to 1e5 and the values were less than equal to 1e9. So at an I, if you were tried to find all the sums and all the mins, this would be O of n for calculating the sum and the min, and n possible I, so it becomes n square, which won't run, right? But here we can see that this is just prefix sum obviously. Literally the problem states this. So this can be calculated in a running fashion. And for the suffix minimum, we can do a reverse iteration and compute the suffix minimum from I to in a, let's say in a vector in an array sfx. We can compute a suffix min. One sec. In a array suffix sfx, we can compute the suffix min sfx I is equal to the minimum of I to n minus 1, right? And then this problem just becomes, where is this? Then this problem just becomes at some I we get the prefix from 0 to I, this part, and then the suffix from I plus 1 to n minus 1, which we have already computed in this reverse loop, initialized to some arbitrary infinity, 29 plus 7 here, and then answer also to a minus infinity since it's in a long, right? And then we just get the score and maximize across all rest. So this is O of n time and space, which was fairly fast, I'd say. Yeah, ये क्या हो गया? हाँ, a mistake I made during the implementation was I was checking for the final index as well. Like I was at n minus 1, I was doing the check for suffix I plus 1 becomes my infinity value, so it was giving an inconsistent result. And also this thing, I had the wrong operator here. Okay, so the second problem is alright. So basically the second problem, what it says is there are basically we have two requirements we need to fulfill. Let rec1 and rec2, right? And we have three items. Let's say item 1, item 2, and item 3. This has a cost 1, let's see 1, cost 2, let's see 2, and cost 3, let's see 3. And if we buy one C1, we get one requirement 1 fulfilled. Same with C2, we get one requirement 2 fulfilled. But if we buy one C3, we get both of these, one requirement 1 and one requirement 2 fulfilled. So we had to find the minimum cost to fulfill both of these requirements, and fulfilling them means the requirement the number of C1s not the number of C1s, the number of requirement ones which we fulfill are greater than equal to this, and the number of requirement 2 which fulfill become greater than equal to this. So this is basically just a case analysis problem. Obviously, like in the problem statement itself, like in the sample case, there is a obvious solution, right? If the C3 is extremely optimal, like here C1 is 3, C2 is 2, and but C1 is 1, right? Which means obviously like I buy one C1 and I get both of these. But if the cost is less as well, right? So initially I was trying to do some like if this then this, but then I realized there are not many cases. So the first case is we only buy C3. And for this case, since we have to fulfill both requirement 1 and requirement 2, and C3 provides us one of both, right? So the number of items we will need to buy will be max of rec 1 and rec 2, right? Since once we buy this amount, we will have fulfilled these both. Like the higher one will be fulfilled exactly, and the lesser one, there might be some extra values, but the problem states that at least is fine. So we go like this. Another possible scenario is we just use these two exactly. Like again in this case, once we have fulfilled this scenario, the max one, there is no need to buy more, since it is obviously going to be a loss of us and the requirement is already fulfilled. For this case, and in another case, there can be a possible solution where, let's say, C3 is some value which is like the sum of, let's say, this and this, or slightly greater than that. So here you would observe that if we exactly buy C1 of rec 1 and C2 of rec 2, then we can also fulfill a requirement. C1 into rec 1 plus C2 into rec 2. So doing this, if we do this, obviously we will have rec 1 amount, and since each is C1, we get this cost, and for rec 2 we get this. So this is also a possible division. And the third case here is like which would need to be enumerated. One sec. Is like you can buy some C3 which will get you to a level, and then for the remaining ones you pad them using the, let's say this is C1 and this is C2. The buying a C3s got us to a level together, and then individually we complete with buying C1 and C2. Now here an important observation to make is how many such C3s would we buy? Obviously we can't enumerate on them all because it's up to 1e9. The need is up to 1e9, so you can't enumerate on them all. But then a thing which we can do is you can make an observation. Let's assume like we have, again we need to do, and I'm doing R1 instead. So for C1 we have R1 requirement, and for C2 we have R2 requirement. Let's say we buy some X amounts of C3. So now our requirement, basically on both of the 1s and 2s, the items, we have reached the X amount, right? Since we have bought X amount of this C3, and for the remaining R1 minus for the remaining R1 minus X, we buy them using C1, and for the remaining R2 minus X, we buy them using C2. So the total result comes as C3 into X plus R1 minus X into C1 plus R2 minus X to C2. Now we need to find this X, right? And if we move this equation around, it comes as X into C3 minus C1 minus C2 plus the remaining equation. So an observation to make here is like, assume we have bought, if we have already bought X, and like if we have not completed, like completely bought one of these two, like if X is not equal to R1 or R2, obviously we will have to reach the minimum value first, right? So let Mn be the minimum of R1 and R2. Obviously we will have to reach the minimum threshold for this first, right? So what I claim is, if this case were to be optimal, where we buy X, where we reach level X using C3 and then buy the remaining R1 and R2 individually, then what I claim is this limit is to completely fulfill the minimum requirement first. And this can be proved using exchange argument as well, because if we have, let's say, not fulfilled this minimum requirement, then we have this condition. But if we, in this equation only, if we fulfill this minimum requirement, one of the smaller, let's say this were the smaller one, this would get to be 0, right? And this becomes, X becomes R1 as well. So the equation becomes C3. So I've got R1 plus R2 minus R1 C2. And here it was plus R1 C1 plus R2 C2. So if we compare these two equations, you would notice that this case is always better. And the third problem, this was not really an observation based problem. The key here was k is less than equal to 1e5, and that the operation is fixed. Basically what we have to do is we have to find the length of this. Let's assume a number, we have to find the length of the smallest number which is strictly consisting of ones, which is completely divisible by k, right? So one observation here is, like, if you are at a number x, how do you go to the next such number? Like if x is, let's say, this, how do we go to y, the next number, which is this, right? So obviously we multiply x by 10 and then we add 1, right? So here if you multiply it by 10, it becomes, my bad, 1 1 1 0 and then plus 1, so it will become this, right? So this is our transformation thing of how to change the number. And the other thing is, since this x has to be divisible by k and this number has to be divisible by k, we also need to maintain a residue, like the current number mod k. And residues work across multiplications and additions as well. So like if we had this x, let's say if the current residue was some r, to convert it into this, we will first do this operation. So r is equal to r into 10 plus 1, and then we would do mod k again. And if this r equal to 0, then that means, like, we would also track the number of digits. This r is equal to 0, then that means return the number of digits, else you loop back, else you continue this. Now the thing here is, how long would you continue this loop? Since, like, assume like there is a case, it is stated that there are cases possible where no such number exists, so you return -1 in those cases. So what would be the terminating condition for this? Again, an observation to make here is, assume you reach a residue r. From there you go to some, let's say this is r0, you are at a residue r0. From there you go to r1, then from there you go to r2, and then from there you go to r3, and then you return to r0. Again, if you do this operation, you would go to r1 again, right? And then basically it's a cycle. This residue, the residues given a fixed operation form a cycle. So if we track all the residues we have reached currently, and if, like, let's say we are at a r0, if we are at a residue which we are already seen currently, that, and we haven't found our answer already, that means, like, if we continue doing our operations from this point, we will again reach the same point, and that means we are stuck in a cycle. So, and if for a given k, the residues can be from 0 to k minus 1 only, right? So what we can do is we can create a array. I use this global array, which I should, like, you could have used a set as well here. I'm pretty sure a set would work, since it's, 1 second. Just count number, right? If we haven't seen this number, then you insert it. This line isn't required anymore. If it's divisible by 0, that means we have found our number. Else we do the operation and go to the next number, and obviously the number of digits will increase by 1, since the operation is this only, multiply by 10 and 1. At the end, if it's not divisible, you return -1, else you return the number of steps taken. And this is 3 6 minus 1. It is working, but yeah, the runtime is like way slower. This is 24 milliseconds. This is 531. Here what I did was, basically you create a global, since we just need to see if we have seen this or not, right? So we can use a global visited or a seen, whatever array, to track the seen stuff and the current number of stuff, which now residues which we have visited. So for every visited one, you put it as 1, and then you roll back all the changes. So this portion guarantees that you won't have to reset the entire array or vector to the initial state, since you're only resetting the states which you have visited here. So this was a micro optimization for Q3. And Q4 was straightforward as well. Basically, given a low to high range, we need to find the number of numbers which fulfill this requirement. either 2 digits and not either, both of the requirements should be fulfilled. It contains at least 2 digits, and the sum at even is equal to sum at odd. So obviously you can't iterate on all numbers since the range is large, but this constraint, how many people have solved this right now? Done. This problem is basically begging to be solved by digit DP, since this is a fairly like a common digit DP pattern where given a range. 1 second. The digit DP, common digit DP pattern is given a range L to R. Find the number of numbers which fulfill a function in this range L to R. So here, since we have to just find the count, what we can do is we can write a function fr minus fl minus 1, which will work in prefix sum using the prefix sum intuition, right? So assume we have to find this range. We can, if we have to find the count in this L to R, we can find the count in 0 to R and then 0 to L minus 1 and then subtract this, so we get the result we want. So for this, the digit DP states were trivial as well. We need to track the sum at even, sum at odd, and the traditional tight and index for the digit DP state. The mistake I made here was in the function calling, which is very stupid. And for digit DP, like it's usually, I should have started with this one. It's usually recommended to use a, what do we call this, a global DP matrix instead. And just reset the portion of the matrix which will be used. Like here, if we have a, let's say, number 1, what is this? If we have a number 1, 2, 3, 4, 5, and the number of digits here is 5, right? So even in the worst, obviously in the worst case, the sum here could be, I think, 9, 9, 9, 9, right? Which is 36. So basically, like for this case, the largest 5-digit number would be 5 9s, right? And the sum here is 45. So for the sum upper bound, I just took this, it's the number of digits into 9 for the sum limit. You reset the matrix to -1 for the memoization, and then you just call that DP. At the end, we only return 1 if there have been some numbers placed. Yeah, I don't think this is required as well, because even if we overcounted, since we are overcounting and subtracting on both the sides, since because of this subtraction, the overcounted region will also get fixed. Like if I submit this should work as well. Yeah. So here you get the upper bound based on tight. If it's tight, then you get the correct digit, else it's 9. And then for every digit, you get the next states, you get the parity of the current thing. I'm doing I+1 since they stated that the first leftmost digit is position 1, so it's odd. So just you just need to fix the indexing. And then yeah, it's just you pass the next thing to the result and then add and then memorize it. I'd say this was fairly straightforward. Here the mistake I did was like forgot to memorize because I was debugging a silly issue. And here the thing I mentioned regarding the matrix, like here I was using a vector, right? And vector is heap memory, which is slow, and you are making the vectors again and again, which can, like here again the complexity was, assume we have n digits in our number. Our complexity is 2 for the tight into n, since we are iterating on all n digits, into 9 into n squared, not squared, yeah, squared, where this is the sum limits of the sum, even and the odd sum. This could be done by half as well, since yeah, this should have been actually not this should have been, since only half of the but yeah, that can be done obviously, since like if we have a, let's say, 5-digit number, here only these indices are contributing to the odd sum, right? The rest are contributing to the even sum. So you can like make the state smaller to make the runtime quicker, but this also, the complexity of this is 9 into 81s, 162n square, right? And this is a constant, and n is the number of digits, so we have 15 digits at the worst case. 15 into 15 is 225 into 162. So this is the worst case for one test case, the number of operations. And again, this will be done twice since we are doing the low minus high thing. So this, in my opinion, should have worked, but since LeetCode like sums the things across all test cases, you had to make this optimization. Again, let me know if something was not that clear. And obviously I'll try to timestamp the things so you can like view the specific stuff, and the screencast will be available after this, the editorial. All right, I'll see you. सबसे पहले एक तो ऑब्वियसली सारे फिफ्टीन डिजिट्स है ना, तो 15 मतलब 9 × 15 है। don't see him. Right. Leftmost digit. Okay, wrong method. It is high and it's low minus both inclusive or taken prefix on HLS. And right, NIE अपना I person D digits सारे U digits सारे and NIE all emblem is usually मुझे 3 digit पे जा ही नहीं रहा. हाँ ऐसा क्या है? 3 digit पे जा के नहीं रहा. टाइट वन. अरे भाई यार तेरा of LeetCode.